The story is, and it's true, that as far as classical mechanics is concerned, that second sequence of states is perfectly compatible with the laws. And it's easy to get that state. If the first is compatible, you just take all the momenta of the particles and reverse the direction of the momentum and get the second sequence, assuming this is all isolated system and not interacting with anything else. And this is long a puzzle. It was a puzzle to Boltzmann. And especially since in this thermodynamics, there's one sort of super law, the second law of thermodynamics, which says that a certain quantity, which can be characterized in terms of heat and work and so on, that inevitably increases in all processes that are more or less energetically isolated from the rest of the world, or increases in the universe as a whole, the so-called entropy. Entropy basically is a measurement of how much useful, the inverse of how much useful work there is in a system. So energy can sort of be in a form where it's more or less it's heat, it doesn't do anything good for you, it can't be used to do work, or in a form where it can be used to do work, like the energy, the chemical energy that's holding together the bonds in gasoline in your automobile. And in any process, entropy never decreases, typically increases, says the second law of thermodynamics. Well, this was a puzzle, because on the one hand, the fundamental laws about what everything is made up out of, the atoms, says that reversible processes, temporally reversible processes, are perfectly possible. On the other hand, we never experienced them, and one of the other laws says, the laws of this macro law of thermodynamics, says that they don't happen. Why is that? So that was one of the hard problems in physics that Boltzmann confronted. There's another problem that isn't much noticed. I don't know who really noticed this first. Or even that if you were to ask a physicist about this, what quite a physicist would say. I have physicist colleagues that I've discussed this with, and they'd say, oh yeah. But even thinking about the motions of the planets, if you think about the planets as being made up out of atoms, particles, point particles, as Halley, for example, might have thought, those particles could be on trajectories that, from a macro point of view, when you look at them, look at the whole thing through a telescope, it looks, just the way the moon looks. And even if you made macro measurements, you would get the same results. However, those particles are in an aberrant state, weird state, where in 15 minutes, they're all going to leave the moon. They say, no more moon. Those kinds of situations are perfectly compatible with the dynamical laws. And in fact, there are a lot of them. There are continually many such states. There are continually many, what we think of as normal, good states too, ones in which entropy increases and the particles stay together. But there are continually many weirdo states also. So these are two hard problems for physics, how to get rid of the weirdo states. Now this is a picture which I can't show you. Okay, actually it was the breaking eggs. It was the refrying, the unfrying of some eggs that we made a video of. Okay, so here's the second law of thermodynamics, which I more roughly described to you. And if you think about it for a second, philosophers who write about physicalism should know about these hard problems for physics, because they make the hard problems for physicalism all that much harder. Because all of those processes that we're interested in understanding, those physicalists are interested in understanding how they fit into the physical world, all of them really are temporally directed. They involve temporal direction, and they presuppose that non-aberrant realizations. Especially the direction of time is there. Okay, so here are these two guys. Now, I got pictures of them kind of looking at each other, but they don't look very happy. I don't know that much about Mach, but Boltzmann was especially an unhappy guy. I've been to the spot where he committed suicide. You know, when you take a course in statistical mechanics now, It's among, at least it's part of the law, and this was true in the course I didn't take an undergraduate course actually in statistical mechanics, but I did go to graduate school, and there's a famous teacher of it, and they begin the course always by telling the students, warning them that the inventor of the subject was so troubled that he committed suicide. He committed suicide initially, actually, right up near Torino, where the famous Torino elegies were written by Rilke. So right on the coast, it's not very far. Boltzmann was an interesting guy. But I heard that the reason he committed suicide probably wasn't because Mach didn't like him, or didn't believe him, or his attitude, I mean, ultimately Boltzmann certainly won this dispute about realism about atoms. And in fact, he committed suicide in 1906. Had he bothered to read papers that were being published in 1905, but it's unclear to me whether he knew about them. I don't think he did, especially Einstein's paper on Brownian motion. He would have seen that he was totally vindicated. But anyway, it was more that he was just an unhappy guy, and also he couldn't make up his mind about where he wanted to teach. He kept wanting to get an offer at the University of Vienna, and then when he finally got it, he couldn't make up his mind. There. Okay. So for Mach, in fact, reconciling thermodynamics and mechanics, I don't know that Mach ever wrote anything about this. Needless to say, I'm not a Mach scholar. I heard today that when it became a little bit known nearby that I was going to be a speaker on Mach, a note was sent, said, "What? That guy doesn't know anything about Mach." I found out a little bit. Oh, I know a little bit about Mach. So I don't know whether Mach ever wrote about this problem. It was definitely in the air in physics a lot at the time. And Mach outlived Boltzmann by a bit. So I don't know. But for him, this wasn't a big problem because he was an irrealist or instrumentalist about atoms. Just as a quick remark, I personally see the history of physics, the history of science really, as a giant struggle between instrumentalism and, I mean, nothing novel about this, but I think it's one of the very good ways to teach and understand the history of science is a kind of battle on many degrees of this between instrumentalism and realism. And Mach and Boltzmann were on different sides of that. So you can see that Mach wouldn't have gotten all upset about this problem, not believing that there were atoms, and so thinking that the laws were just nice codifications of observations. It's the observations part that I don't go along with Mach, but I like the codification part. So here's Boltzmann's grave. It looks pretty impressive. That's in Vienna. So it turns out that Mach, when I looked this up this morning, I didn't do this morning, that he was sort of dug out of his grave and thrown away or something. I guess that's what's meant by his grave was cleared. So I don't know what happened to poor Mach's body, but this is the monument in Munich. Okay, so Boltzmann had an idea. I'm going to speed up a little bit, otherwise I would really take up the time. So Boltzmann's idea, as many people here know, was to say, the second law of thermodynamics may not be exact. It's probabilistic. If we imagine that there's a kind of uniform probability distribution, it is basically a uniform distribution over all the states, as I say, the positions and momenta of the particles that could realize a macro condition, like a piece of ice and some warm water, then we will see, it will follow from the dynamics, the Newtonian classical mechanical dynamics, that the measure on this probability distribution, the measure of states which evolve in a good way, that is to say, in accordance with the law of thermodynamics, second law of thermodynamics, is basically 1. So in a certain sense, almost all states will evolve well and won't be aberrant states. Almost all will be non-aberrant states. Now, when I'm using the phrase almost all, I don't mean that in an accounting sense, because in a cardinality sense, they're continuing to be many. It's in the measure theoretic sense of almost all. And that's what's needed for undergoing probabilities. And there are a lot, Boltzmann tried to give arguments from non-probabilistic, what we thought it was non-probabilistic assumptions for this conclusion. It was a very famous argument for this, it's much discussed. I don't think any of these are really successful. You don't get probabilities out unless you put some probabilities in somewhere.